Hello, everybody, and welcome to this month's Future in Space Hangout. My name is Tony Darnell, as evidenced by this really cool lower third that I just put up here from deepastronomy.com. And today we are going to be talking about the low-temperature universe. We had a little bit of a discussion before I pushed the broadcast button that there is several layers of the universe. There's cool, there's cold, and we're going to talk about those distinctions, I suppose, as we go on in our hangout. But we've got members today from a brand new telescope that's being planned out now, the Origin Space Telescope, and I have members of the mission or the team here, both of whom are from the Space Telescope Science Institute working on this telescope. So we will learn not only what the low temperature universe is, but how we're going to observe it and why we want to observe it. So all of those things are coming our way in this hangout. And I think if you're watching this, then you know it's being streamed on some platform, but I'll let you know that we're on YouTube, we're on Facebook, and today I'm doing on twitch.tv/deepastronomy. That's Facebook/deepastronomy, and of course youtube.com/deepastronomy. And I'm looking at the live chat window right now, and I'm already seeing a lot of people here on the chat, which I will get to in a minute. But first I want to introduce my two co-hosts, which I have in this hangout. One is Dr. Alberto Conti. Hello, Alberto. How are you?
Hi, Tony. It's good to be here, and a shout out to Harley, who couldn't join us today.
Yeah, Harley couldn't make it today. He was busy, and so helping us out as she always is my good friend and colleague, Dr. Carol Christian. Hi, Carol.
Hey, how are you?
Also known as Harley 2.0.
Harley 2.0.
Harley 2.0, right.
All right. Okay, so these, Alberto, since you're with me on these hangouts most of the time, why don't you give us a little bit of a indication first of all, who's making these possible, and what are we doing here in Future in Space Hangouts?
So that's a great start, Tony. So these Space Hangouts, Future in Space Hangouts, are made possible by the two AAS, so the American Astronomical and Astronautical Societies. So thank you for their contributions. And the scope and the goal of these Hangouts is really to bring up to speed, the general public about what's going on in space. In particular, today we're going to talk about astrophysics, but in general is, our future as a species in space. What are we doing? What are we learning? And how do we move the species forward in learning about our beautiful universe?
That's right. And today we are moving forward in looking at the low temperature universe. Now, I'm going to get clarification on this, but I don't think it's the same thing as looking at the infrared universe, but I'm not quite sure if we're looking at infrared wavelengths or what yet. So we're going to find out from our guests. But let me just let you guys know that I'm hoping that these hangouts become a lot more interactive in terms with our guests. So I see that, like I said, I'm looking at the live chat here on YouTube. I'm going to read your comments out. So help me out here and ask our guests questions. I'll be sure to read them out as quickly as I can and sort of help you guys or help me drive the hangout a little bit. I'm also looking at the Future in Space hashtag on Twitter, but I'm not looking at it constantly. So if you're on YouTube, I'd appreciate it if you could use that as well. But I'm already seeing Galaxia and Philip W., John Suffel. These guys are my UK contingent and the Netherlands contingent. So these guys are all here. So welcome, guys. It's really good to see you. Scott Jason and Alberto Conti's in there too for some reason. That's odd. Adam Synergy. We are looking forward to getting your comments and questions. So let me introduce our guests. Joining me today is Dr. Klaus Pontoppidan from the Space Telescope Science Institute. Hi, Klaus. Welcome.
Hey, Tony. Good to be here.
Yeah, and he is he's a project scientist on JWST as well as a member of the Origin Science Technology Definition Team, the STDT team. Not to be confused with the STD team. So there we go. We want to make sure we get that clarified here. Also joining me is Dr. Margaret Meixner. She is the community chair of the Origin Space Telescope Study. Hi, Margaret.
Hey, Tony. Thanks for having us here.
It's really good to have you here. Let me start with you, Margaret. Give us a background on just what this Origin Space Telescope Study is all about. What is it?
Right. What is it? Well, Every 10 years, the astronomy community does what's called a decadal survey, where they survey what the most important scientific questions are and how to achieve them. And they write a report called the Decadal Report. And what NASA is doing is seeding 4 different large-scale flagship mission projects. One of them is the ones that I'm leading, that Klaus is on the team to help out with. It is a large, cold telescope. And it's going to operate from kind of like 5 microns out to 500 microns, studying the cool nature of the universe.
5 to 500 microns. Is that the far? What is that? Those are infrared wavelengths, but they're
infrared wavelengths. So it goes. I mean, I guess people would say from infrared out to kind of far infrared submillimeter wavelengths is what astronomers would call it. They have, they give little names to every little part of the window, but it's cold and it accesses atmospheric windows that we can't see from the ground, and that's why it's a space mission.
Okay, good. Well, aren't all telescopes that go into space cold? I mean, how is this one like colder than most? I mean, JWST, for example,
is pretty cold.
Is this colder than that, or you got to get to submillimeter wavelengths? But I know that ALMA, for example, can look at submillimeter wavelengths. So,
well, we want to look at these wavelengths at a very sensitive level, and to do that, you want to get to what's called the astrophysical background. James Webb is a passively cooled telescope, but it's at 35 Kelvin. So at the mid-infrared wavelengths, it actually has emission from the telescope that causes noise, if you will, for the astronomical measurement. It causes what's called what they call a background. And what we want to do with Origins is make it so cold that it is the only background is the astrophysical background, like the ZODI background.
Like the what background?
So the zodiacal light background.
Right. So basically, what you're saying is that even JWST at 40 Kelvin or 35 is just too warm for the science you want to do, and so you get down to.
Yeah.
Correct.
I mean, it would absolutely kill if we went. I mean, so the closest telescope that's been launched prior was an ESA mission called Herschel.
Yeah,
it was a long telescope, but basically, the telescope temperature was the main background. It wasn't the astrophysical background.
Yeah.
Okay, I got to correct something before we get too far along. I said the Galaxia was representing the Netherlands. That's not true. She's from Belgium and representing Belgium. Sorry, Galaxia. But you are there. I mean, I'm just to be fair. Just to be fair. Well, I wanted to get it right.
And we have European observers helping us out with this, including doing one of the instrument studies.
Okay. Well, let's talk about the science itself a little bit. Klaus, let me get you in on this. Tell me a little bit about what you're doing on the science technology definition team. Apparently, correct me if I'm wrong, but this is early enough in the mission where you're still deciding what you're going to put on this space telescope, aren't you?
Right. Well, the process was that we sort of basically the charter we got was, think about the coolest, the best far infrared telescope you might like. And in particular, think about what kind of science, the most exciting science you can do in that wavelength range. And then we'll see what kind of telescope we need to accomplish that. So my research field is in the formation of planets. It's especially in the composition of the material that forms planets. I'm interested in things like water. And that's one of the key things that a far infrared telescope can observe in space is water. And so it's true, as Margaret said, that there have been previous missions to do this, like Herschel, for example, that the Europeans did, which was a warm telescope. And JWST is also going to be able to do some water, more the warmer kind.
Okay,
now,
you're saying water. You're saying water. What exactly do you mean? Where you're observing water vapor in other atmospheres? What do you mean when you say water?
Right. Well, we're interested in how do you get water to habitable worlds ultimately. We have water on the Earth. It's essential for our existence. It got here somehow. So in the universe, water is really everywhere. It's in the very cold interstellar medium before we form into stars. It's part of the star formation process. it gets transported into the disks that eventually form planetary systems, and from these disks it somehow gets transported into planets, and in particular into planets that may end up having life on them. And so in order to understand that whole process, we have to have observatories that are capable of observing water in all these different environments. So really an Origins tries to do this. It's really from the cold interstellar medium all the way to planetary atmospheres. The Origins Space Telescope will also be looking at exoplanets and determining their composition. JWST will do that too, but Origins is a bigger telescope, and it will have dedicated exoplanet transit instruments. And so the idea is that it will do even better.
Now, the stage you're at right now with the Origins Space Telescope is in a similar phase where both JWST had to go through, and maybe Alberto, you can comment on that, as well as Hubble, right, Carol? Back in the day, at some point, people were, before anything got built, they had to decide, well, here's the science we want to see, and here's the kind of telescope we need to build. Is that correct? Is that how it works? And that's sort of where we are with Origin?
Right. So I think Margaret mentioned at the beginning, the astronomical community every decade goes through a process where they sort of rank, if you will, for lack of a better word, what is the best science for the next decade, right? So JWST was a result of this, Hubble was a result of this, Spitzer was a result of this. So there's a long tradition of fighting out the science, if you will. And so the Origins, together with the other three science definition teams, are looking at potential candidates for what might be supported during the decadal for future large missions.
That decadal survey, man, we've talked about it so many times on these Hangouts. That's like the Bible, isn't it? Well, maybe for lack of a better word.
The other thing I think is really interesting about the decadal is that, in a moment of time or several years while you're constructing, the community puts forward what they think the state of the science is going to be in 15 years when the telescope they're advocating is going to be launched. And so it's a pretty interesting exercise as we go through the years to see if our predictions are right. Now, we know we have to go to the far infrared. We all know that already, but exactly what we will know we kind of know what we're going to know because we're here when JWST launches, but Origin Space Telescope, we have to make our best guess on how we progress through our science and where we need to be when it launches.
And that's a great point, because when JWST was thought of, for example, if you take a look at their mid-90s, we didn't know, we knew a few exoplanets existed, so we didn't know we could use the telescope for doing what we think we can do with JWST. And so you're absolutely right. That's sort of a bet that the astronomical community puts on the science that will be relevant also. Which brings me to the other point, which is all of this. Decadal missions have to be wide enough in scope so that they can answer questions for which we are not ready, or for which we don't know the answer to, so to speak, right?
Right, and that's a very interesting point, because when we did the science exercise last summer, some part we were actually just trying to decide between single aperture and interferometer, but we said, come up with the science cases of questions that you think are viable in, post JWST, post W first, almost been operating for 15 years, large ground-based telescopes. Think about what all the interesting science questions and come up with questions that only this observatory can answer. And that was the goal of the exercise. And that literally is what you have to do when you design one of these, because you want to, NASA's going to take a decade to build it. Mm-hmm. It still has to be doing something new and discovery worthy when you get there. And that's the other goal of the study.
Okay.
Yeah, it's actually an interesting. There's an interesting challenge in Origins, and that is this incredible increase in sensitivity you get when you have such a large cold telescope. As Margaret pointed out previously, there was Herschel. It was a 3.5 meter telescope, but it was warm. There were cold telescopes in the far infrared before. Spitzer was a far infrared. It had a far infrared channel in it too. It was 85 centimeters. We're talking about a 9 meter telescope now. So the increase in sensitivity you get is like a factor of 1,000 or more.
Wait a minute, you said 9 meters?
Yeah.
Yeah, we should go over this because it's really cool.
Yes.
Right. So you get this many orders of magnitude of increase in sensitivity. So it's in the far infrared, for far infrared science, it's analogous to, up until now we have crossed the English Channel. If we build the Origin Space Telescope, we can cross the Atlantic. It's an enormous change in sensitivity, and so that's this giant new discovery space. We just scratched the surface at our galactic neighborhood, and now we can go to the edge of the universe and we go across the entire galaxy and study things in great detail and huge numbers of things that we just don't know what we're going to see.
Okay, I want to go ahead.
Go ahead.
No, go ahead, Margaret. It's okay.
I was just want to follow up. He says you'll see the edge of the universe. I mean, that actually was one of the science cases, is that we want to see to the point where galaxies, so James Webb will see the first stars, first galaxies, but Origins, we're designing it so it will see the formation of those first galaxies.
So, okay, JWST is at the beginning of the Dark Ages, right?
Yes.
That's what they're calling that.
Right, the beginning of the first light.
That's right. So this is right when stars began to shine, galaxies began to form, and you're talking about going back before that.
Yes, going back to when they were forming. So in the cosmic dark ages, looking at the collapse and formation of the first protogalaxies.
Oh, wow. Okay. And this is going to, I just want to make sure I understand this. This is going to be a 9-meter telescope in space.
Yes.
And you're going to, are there designs for it yet? Is it going to have segmented mirrors? Is it going to fold up? What's going to be the...
Yes and yes.
Okay. But apparently all of this is still getting worked out. Am I right?
Yes. Yeah.
Okay.
I mean, right. There's no launch vehicle that will take a monolithic up.
Right.
And even if you could, it's not clear that that's the best option for, to do what you want to do. So, I mean, things will be segmented. I mean, how? There's a concept study that we're working on. The goal in the concept study is to come up with enough design detail to be able to show what the technology tall poles are, how you would get through them in time to build this for the next decade. And that's the engineering part of the exercise. When I asked them, I said, gosh, this seems really detailed. They said, we need this to figure out the important points and also to get an estimate, a rough estimate on cost. Right. Because that is also part of creating a credible mission is.
Okay, well, I want to talk about the cost and the schedule maybe a little bit later on here, but let me get to a couple questions. Adam Synergy is asking, is it going to have a spectrograph?
Yes. Do you want to talk about the spectrographs, Klaus?
Yeah, it's going to have a lot of spectrographs.
Spectrographs.
Yes. We'll have 5 instruments, and I think all of them have had some sort of spectrographic modes. It's actually really important for the galaxy. It's important for many things, but just as an example, it's really important for the galaxy, for the super high redshift galaxies that Margaret was talking about, right? Because you run into what's called the confusion limit in the far infrared. That is that even for a large telescope, you have so many galaxies. You take a deep image of the sky with so many galaxies that they all overlap each other. And you can't pick out any more individual galaxies. It just becomes this pile of sand, right?
Right, and because you're going so deep.
You're going so deep, right. Yeah. And in fact, galaxies of the universe is super bright in the far infrared, and that's part of the problem, right? So very, very quickly, you just your whole image is filled with galaxies.
So
right?
by comparison to say the ultra deep field that Hubble took, where the galaxies there were a lot of them, but there were probably. But you could tell the indistinct ones. Here, is this a picture of one now?
Yeah, so that's I think you're showing a field from Herschel, which is a deep field, and you can just see, and this is a smaller telescope, but you can see how it's filled with galaxies. And if you zoom in on this, there's no spot in this that doesn't have a galaxy.
All right, hang on. This is a deep field from Herschel.
From Herschel. That's right. It's a real deep field, and you do this, and the sky is just filled with far infrared emission from galaxies.
Wow.
At every point.
Okay.
We are surrounded.
That has a pretty high confusion limit, I think, right? Is that the way you would
describe it? Yeah, it's confusion limited. Yeah.
It's confusion limited. That's how I live my life. I live my life that way.
Exactly. It confuses us.
Yeah. What it means, it doesn't help you to go deeper because you don't know, you can't pick out one galaxy from the next. And so the way that we get around that with Origins is we spectrally disperse the light from all these galaxies. So now a lot of these galaxies, the light have very strong emission lines in them. And all the emission lines from a certain element or a certain molecule get redshifted depending on how far the galaxy is away. So if you have 2 galaxies that sit right on top of each other, you can actually separate them by taking a spectrum of it, because one will have a spectral line in one place of the spectrum, and the other one will have that same spectral line in another part of the spectrum. So you break through the confusion limit by having a spectrograph.
Oh, I need to remember that. I want to see.
That's just one example.
Right. That's true. But actually at 9 meters, at the, like, let's say at 50 microns or 60 microns, they'll be able to, even the continuum, to actually separate and break the confusion limits. At the longest wavelength, 500 or whatever, that's, that won't be possible. But at the short wavelengths, for the first time, we'll be able to actually separate those galaxies. So that deep field, you will see some spaces with something as large as Origins.
Okay, compare this telescope to the field of view of this telescope. Well, you showed us the Herschel deep field. What's the field of view going to be like compared to Hubble and JWST? Is it going to be narrowband? Is it going to be real tiny field of view? Is it going to be a wide field of view?
It's going to be this big.
It's going to be that big. Thank you. Okay, it's going to be that big. Everybody clear on this? Is that what you did in the science definition team? The science technology definition team? Here's what you guys did.
We need a field of view this big. I'm not on the science.
And we need stuff with lots of knobs and wires. And we need to put in things. Oh, let's put in some gold because that's cool.
I was just going to say, I just want to make a little analogy of what Klaus was talking about. It's like having a bunch of screens at different distances. And by selecting a particular line, you can say, I'm looking at that screen, or I'm looking at that screen. But if you put them all together, you just get a mess. And that's the confusion.
So this will be primarily a spectrographic instrument then. Am I reading this right?
Well, no, there'll be imagers on it,
okay.
but there will be really good spectroscopy on it.
Yeah.
In what way will you rely on? I don't want to say AI, but I will say automated processing. Like I know that for a lot of people, even today, using astronomy images, they use software that deblends the galaxies. There could be two galaxies superimposed on the other, and the software tries to deblend those. And Carol has already said by using the spectra, you can see which one you're looking at. Does that help with deblending? But what about the optical ones? Can you deblend those as well? Or are you using any automated software to do that?
Oh wow! Well, you're into operations, and we're doing stuff. We haven't thought that far.
We're still,
but that's an
we're still going this big on the field of view. Okay,
so they're gonna do this much analysis. That's it.
That's right. So this much analysis. Got it. Understood.
We are thinking of operations though in the design. We're not just kind of building hardware and thinking about how it's going to be used, because we need to make sure lots of exciting science gets done, not just one thing.
Okay.
Yeah.
Philip W. Oh, go ahead.
Maybe I can just add one point to that, and that's so one of the things that we really like this observatory to be is to be a big data mission, and for that you do need a lot of special processing. What do you mean by big data mission? So, for example, there are missions that are very like Hubble or JWST are sort of very pointed missions. You look at a small field, you look at individual sources. It's sort of a very meticulous
point
thing.
And shoot. That's right.
Point and shoot. And so you get a lot of data out, but at the end of the day, you do. I mean, it's still maybe a manageable amount. There are other missions that are really, big survey missions that take images of the entire sky, and you get this enormous data set. And it's not so much an issue of when you do a science experiment. It's not just so much an issue of designing your science experiment and then go and observing your object. It's more like you already have all your data and you try to pick out the little bits and pieces of the data that's interesting for your science. A far infrared mission, if it's cold and so sensitive as Origins, it becomes very fast and very quickly you can end up with a very, very large amount of data. And so that's expectation for this as well.
Okay. Philip W. is asking, did the survey take into account NASA's SLS or SpaceX heavy lift in terms of the size of the telescopes scientists want to launch?
That's a great point.
Well, I would say that currently the first constraint we've put on is to say, okay, let's look at a 5-meter fairing and how big of a telescope can you sort of fit into that. However, now that they're adding things on, things are getting heavier and all that. So, SLS is not out of the realm of possibility, but that hasn't been something we're looking at the moment. We're looking at launch vehicles that are in existence now,
Right.
and presumably will still be there by the time this launches. But it's possible.
Right.
And I think, Margaret, what that means is that, so JWST just fits into something like that with one fold. And so to have a larger telescope fit into that before we have to fold it at least twice.
Oh, yeah, it's all the way around.
But I guess the other reason why you cannot assume SLS will be there is also because they haven't done, they're going to do their first test in 2019. So, which is relatively late for you to put it into your mission. So you have to do whatever you have available now, even though you're going to launch at the end of the next decade. Right.
Okay, but wait a minute. With JWST, Alberto, there were things that had to be invented.
Right, and I don't think this is any different. But remember, the JWST launch vehicle, is Ariane, because we knew that we didn't have anything larger than that, and that was constrained, as Klaus was saying. Really effectively the size of the telescope.
Is that happening? By the way, Klaus, with the Origin Space Telescope, are you guys wanting to do science for which there is no things
technology
need to be invented?
available?
Yeah, technology available, or are you guys picking stuff off the shelf?
Yeah, I think you don't want to start something that's pure science fiction. So NASA operates with something that's called technology readiness level, TRLs, and there are values from 1 to 10, and the higher it is, the more ready it is. So maybe the range is slightly different. And so yes, you don't want to go too low on that. So there's definitely
5 or above, right, or something like that.
Yeah, I think a little lower right now. Yeah.
Right.
So there are definitely some things that need technology development. One important thing we believe is detectors. Right. So, for example, if we're interested in doing a lot of exoplanet characterization, like we measure the composition of exoplanet atmospheres, JWST is likely going to be limited also by the quality of the detectors. How accurate can you separate the light from the parent star of the planet from the light from the planet itself? So we have to improve that to get to get the science out of it that we want. Yeah, go ahead.
No, so I was going to say it's worth mentioning that that typically for missions like decadal missions, the decadal survey takes into account the technology readiness level, and typically they want to see something that can get to what's called TRL 6, which is a technology demonstration in and around the time where the decadal is proposing. So that is not really science fiction. It's something that is in the bank. Maybe you don't have the full solution, but it's something that you could reach what's called TRL 9, which is basically the flight hardware.
So there's this scale that NASA has. It's called a technology readiness level scale, and it goes from 1 to 10. And you pick from that, with 10 being not so ready and 1 being it was ready since the 50s, right? Oh, here we go.
It's the other way around. Yeah. 1 to 9.
The other way around. 1 to 9, 1 to 9. I don't know if you can see it, but
let me see if let me put it up. Keep it up there, Alberto. Let me
I just downloaded it quickly. It's not a great image, but see if I can.
So here's the TRL scale. Yeah, so we've got, I see.
So TRL 6, the 506 is what you want to get in order to demonstrate that the technology is viable, if you will, and that improvement needs to be made. And TRL 9 you can think of as when it's launched, basically. Everything that technology that was developed for JWST will become TRL 9 the moment JWST launches.
Okay.
And successfully.
And we can probably have a couple of things at a TRL 4, I believe, something like that, right. where we know we have to do work, but
that's right.
That's the path.
Right.
All right, well, let's go back to the decadal survey real quick, since we're on TRLs. Now, you guys said this was part of the decadal survey, and we always build whatever's number 1 on the decadal survey, like W first was coming, JWST was up there, and Hubble before that. So where was Origins on the decadal survey priority list?
Oh, we're not there yet. So this is for the
you're still trying to get on it.
Yeah, that's it.
Yes.
Oh.
So NASA has if you will, commissioned 4 studies to put together these things for that committee to review. And this is also to see, because it's hard for decadal surveys to evaluate flagship missions if they have a 5-page report, or to understand that. And so the idea here is to seed them with a number of very well-grounded information reports and hey, take a look at these. What do you like? Why? For all I know, they'll say, well, we like all of them, but we're going to pick this. We'd like to do them in this order. Or, I mean, who knows what they're going to say. But
Right. I mean, so the decadal survey can do many different things. It's not that the charter is not to pick one of these four missions necessarily. I mean, they might say none. They might say we'd like to do all of them. Maybe we want to do some combination. They can do different things.
Okay. Well, Atom Synergy is asking, will it have a sunshade? How is this telescope going to stay cold?
Yes, it will have a sunshade and cryocoolers to keep it cold.
But again, those technologies are coming directly from JWST if you think about it, right?
They are. Yeah. No, and that's why when I asked the engineers, because when I gave a talk on this in Edinburgh a year ago, they said, really, a large cold telescope, how are you going to do that? I was like, I don't know. You're the engineers. You tell me how you do it. And I had 10 engineers come up afterwards and saying, this is how I would do it.
There you go.
And,
right. Yeah, the difference to JWST is that the primary mirror is actively cooled. So it's a lot more.
The primary mirror on
Origins.
On Origins. Yeah,
actively cooled how? What do you mean by actively?
There's something like a refrigerator pump.
So something like liquid helium or something going through it.
Cooler, yeah.
Okay.
Yeah. It won't have, right. It likely won't have, like JWST, for example, also has a cryocooler for MIRI that it's mid-infrared instruments that has one of those, and it's a closed cycle cooler. So it means it doesn't evaporate off helium to cool it. It cycles with a compressor, like a refrigerator.
Sure.
So similar for Origins, but much more of that.
Yeah.
So JWST is going down to, what is it, Alberto,
35 to 40 Kelvin for everything except for MIRI. MIRI has a cryocooler, which actively cools one of the instruments, the mid-infrared instrument, to about 6 Kelvin. So I think what
that's pretty darn cold, and so
that is very cold. But that's one of the instruments. I think what Klaus and Margaret are talking about is cooling actively the telescope itself. These 9 meters with cryocoolers of a next generation that will take it down to the 4 Kelvin operating temperature they need.
Okay, Nick Hardy is asking, is the main mirror going to be segmented like JWST or separate main and secondary mirrors like Colossus? And I guess since you're going to have an actively cooled primary, it's not going to be segmented, is it?
It is segmented.
Of course it will.
So you're going to just have it go
that's
through
how
all
we're
the
going to
segments.
launch it.
You can't fold it if it's not segmented.
Yeah.
And you want to make it light as well, right? So monolithic mirrors are pretty heavy. So.
Yeah. 9 meters.
I mean, you can see on the concept we have right now, you can see there's a lot of JWST heritage in that.
Yeah.
I mean, once you launch JWST and it's successful, then you demonstrate that you can do segmented large structures, deployments and everything. So why not reuse that heritage, I guess, that has been already proven to work?
Yeah.
I mean, it's complex, but it's the next generation that we want.
But I've been learning recently about these segmented mirror designs, and one of the things that they are problematic in the sense that diffraction can really get in the way of a lot of these segments. Even the Keck Observatory on the ground in Hawaii suffers from this. But I guess since you're primarily a spectroscopic instrument, you don't care so much about that?
No. We will, but we're also going to have an off-axis design. So actually, it'll be a lot cleaner. I mean, yes, the segments will have some effect. There'll be some edge effects and stuff, but because we're going off axis, we're actually hoping it's going to be a lot cleaner.
Oh, okay. Wow. I'd love to see some pictures of this thing once you get it more fleshed out. This sounds really amazing.
Right. Also, I mean, you're operating at longer wavelengths, and that also makes
good point. That's right. Okay.
So JWST is diffraction limited. Its requirement is to be diffraction limited at 2 micron. Origins is to be diffraction limited at 20 microns. So there's an order of magnitude there that makes it easier. So that's where we save.
Okay, Capital H is asking, will this see through the zone of avoidance better than we have yet seen? What's the zone of avoidance? Isn't that the thing that JWST can't look? It has to stay in a certain...
Zone of avoidance.
I'm not sure what the zone of avoidance.
I'm not sure what it means.
Yeah, help me out, Capital H.
They need to clarify, but there is a zone of avoidance, which is the zone in our galaxy where you can't see past the center and the bulge.
Exactly. I was thinking that. Yes, we will see that. But are they talking about
that or?
Yeah, help us out, Capital H. Tell us what you mean by zone of avoidance, and we'll get your question again. VDR 1981. Is there any chance that JWST could somehow peer through galactic plane and actually shade some light on the great attractor? Shed some light on the great attractor. Yeah, I'm not quite sure.
Well, we can say no.
Possibly.
Yeah, it's a good question. I mean, you're going to have a lot of background through the galaxy. I mean, it's not one thing is to see through the dust, but there's still dust and it's very bright, so it creates a lot of background. So you're certainly not as sensitive looking through the galactic plane as you would otherwise.
Right. You're going to be able to see better than other telescopes, but I agree the opacity might be too high.
Right. So that's possible. I mean, I think JWST could do it as well, but JWST doesn't have the speed to be able to survey a large area, while Origins might be able to do that. So that's a good
question.
All right, Larry Keys has a couple of good questions too. He goes, "Big data!" Exclamation mark. Yes, indeed. First of all, he wants to know, have you picked the orbit? And second, how much onboard data processing will you have to do? Have you thought about that yet? Where are you going to put it? L2?
L2. It will be at L2. Have we thought about the data processing on board? I think we're at the point where we think something will be needed, but not a lot of definition has gone there yet.
Okay, George Caldwell. Are detectors subject to noise which could distort temperature readings, for example, from the cosmic microwave background radiation? So will your detectors be subject to noise from CMB?
Not from CMB. Right. Sorry, go ahead.
Because that's microwave, and you're looking in the infrared.
Yeah, I think we tend to be a shorter wavelength than what is really affected by the CMB. Right. Maybe at the very longest you start to get affected by it, but generally it would be shorter.
You might pick up. It might be a source of noise in the sense that we want to make the telescope cold enough that we're limited by astrophysical backgrounds. But I suspect things like the zodiacal light will be brighter. If you're anywhere near the galactic plane, that's going to be brighter. If you're anywhere near the I think the cosmic infrared background, there's all those distant galaxies. So I suspect a lot of those other backgrounds are going to be significantly higher than the cosmic microwave background. So it's not going to be the dominant source of noise for us.
Alberto, I can read this chat, right? You're busting on me. Tony is not good at geography. I'm right here.
You said Belgium and Netherlands. You're confused.
No.
Europe.
I know they're not the same, but it
took you quite a while to read that. That's awesome.
Well, I'm scrolling up, and I Philip W. is representing Ireland. Yes, the Republic or Northern Ireland. All right, so I want to get to the schedule. When's this thing going to launch? You're still trying to get on the decadal survey, so presumably it's going to be a while. And how much is this thing going to cost? Any idea?
Well, we are so it'll be like flagship missions cost. So part of the process of the engineering study is to get to a point where you can actually cost it, and so that's part of the goal. So we don't have an answer to your question yet, but invite us back in a year and we might have an estimate for you. But for flagship missions, they have multiple science goals and stuff. They're going to be probably at the same level as sort of, a Hubble, a Spitzer, James Webb, those missions. And you have to, of course, account for inflation. So for present day dollars.
Okay.
So, and I'm sorry to be vague about that. I don't have the
You don't want to be nailed down on a cost before you. Yeah, I get it.
On the order of a flagship as opposed to, a probe mission where it's highly focused, there's one instrument, they're doing one thing.
So that brings me to Urick's question. Urick Mazino is going, maybe you already asked and answered this, but how will reserving time on Origins work? And let me extend that to say, this is not going to be a survey telescope, is it? Is it going to be operated like JWST and Hubble?
Yes.
Okay, so people will apply for time?
Or like WFIRST, because WFIRST is an interesting mission because it does have a large survey component to it to get the science out. So, it's possible that, when if we get to go and we do the formulation for OST, we'll say, part of it will be doing a large scale survey of deep fields. And it's the way we're going to do it is it's going to be released to the community. I mean, there's lots of different ways you could do it. But if you're going to take, let's say, a year equivalent of a year of time on an observatory, that's something that's more of a survey for the community than like one PI project.
Right. But I think an important distinction, and what maybe the question is as well, is that if you have a capacity to make a large survey over a large portion of the sky, you get this big data set, and maybe you can do many different kinds of science with it. We release that to the community right away, right? It's not that there'll be a small privileged science team sitting there with privileged access to that. It's just a different way of taking data. But with the instruments we have now, we have both the survey capacity, and we also have the capacity to do lots of pointed observations. And with a very broad science case, so it will definitely be a community facility.
And going back to what we were talking about before in terms of TRL, we have missions now like WFIRST that will be pretty data heavy. So we're going to build on all the know-how that we're going to build over the next decade or so.
So we're just learning everything there is to know about the universe now. I mean, by the time this is done, I think we're done, right? We can just pretty much pack up our space telescopes and
by the time this hangout is done, yes.
By the time this hangout is done. So capital H did say that the zone of avoidance was the galactic equal to galactic plane, and the great attractor is in that direction. So I guess we answered that.
Yeah, Origins would definitely be able to look through that.
Okay, good. So, okay, well, if you are, so we've talked about the cost. We've talked about the rough schedule. We're looking well past the WFIRST launch frame. When you launch, how long do you want to be up? How long are you planning to be a mission? Well, what's the mission life? Is it 5 years, 10 years?
5 years is, when we turned around and asked the study manager, she says, 5 years is typical, what they designed to, so it would be a 5-year requirement, but, until the wheels fall off type. The only consumable will be the propellant.
Like with JWST.
Even like JWST.
Yeah. Right. Yeah, I think the issue is that if we go and say, well, the requirement is for it to last for 20 years, it gets very, very expensive because you invoke many, many different kinds of tests that needs to be done. And so you just don't want to do that. It's not an affordable thing to do up front, but you can certainly make sure that you don't run out of helium or something like that after 5 years. So like JWST, it can run until it breaks.
Okay, Bjorn Larsen, is the WMAP cold spot colliding with another? I don't understand this question. We may not be able to help you, Bjorn. What is the WMAP cold spot colliding with another universe? What's your take on that cool thing? Do you know what he's talking about? Cold spot and WMAP.
I'm afraid I do not.
I don't either. Sorry, Bjorn.
I have some idea, but that's very outside of my area of expertise. I don't think it's something that Origins will address.
Right. And Klaus can only say things are true. So
that's right. We established that before we started. We can only say true things.
Adam Klaus can only.
Klaus only.
Right. What a relief. Okay. The gloves are off now. Adam Synergy, we will never ever have too many space telescopes. I agree.
Woohoo! I'm in favor of that.
Yeah.
That's right.
All right. Well, I know that Klaus, you at the beginning of the hangout, you said that we were going to be looking at water. We're going to be looking at and Margaret, you said the first stars. This was before the proto-galaxies formed. Any other science that you're trying to get a window into with this instrument? Or are those the biggies? As if that's not enough.
No. So one thing I think that I'll mention this one that we're very keen about. It's the reason that we're going down to 5 microns is there's going to be a lot of work on exoplanets between James Webb, but also there's a specialized satellite called TESS that's going up to discover new things. And there's no way that James Webb is going to have enough time to spend on them. And Origins, the reason we're going down to 5 microns is to have a capability to work on transit spectroscopy to study all these new worlds that people are finding and be able to look for sort of biosignatures by looking at ozone and methane together, which you can get, in these infrared windows.
Okay, expand a little bit on biosignatures. Just say what you mean by that real quick.
It's a spectroscopic signature in a spectrum that indicates the presence of things like ozone and methane. And I'm not an exoplanet specialist, but Lisa Kaltenegger, who is, says that, well, if you have ozone and you have methane, she's one of our co-leads for the exoplanet working group. She says the only way that they know how to do this, the people who study exoplanets knows how to get both those in one spectrum for one exoplanet, is that if there's some form of life.
So these are features in the spectrum of light as the star's light travels through the atmosphere of the exoplanet as it passes in front between us and the star.
Well,
these spectral features, certain ones, you're thinking, or astrobiologists think, might indicate the presence of life, and one of those things would be, say, methane concentrations. And what was the other one?
Ozone.
Ozone. Okay, so
there's the other thing as well is also ammonia, for example, is brought up as an important biomarker. I just want to make one more quick. So when you do transit spectroscopy of exoplanets in the mid-infrared, you're actually not looking at the planet going. Well, you can do that too, but that's only part of what OST will do, to look at the planet as it goes in front of the star. What you actually also do is you do the case where the planet goes behind the star, right? And so when the planet goes behind the star, you see the
reflection
go down a little bit.
Yep.
Well, actually, you see the thermal emission from the planet itself. So the planet, it's not reflection; it's self-emission from the planet. And if, like, for example, the Earth has self-emission. It's a 300 Kelvin planet that peaks at 15 micron, right? So the emission spectrum of the whole Earth peaks at 15 micron.
Mm-hmm.
It's warm, 330. It's a balmy 60 degrees Fahrenheit or whatever. And so you actually see the composition of the atmosphere against the infrared radiation from the surface of the planet.
Is there any of this that can be tested with existing telescopes, whether they're on the ground or in space? Can Hubble help with this sort of, I don't know if you need a proof of concept. Are you guys pretty confident in your algorithms and your abilities to be able to figure these things out with the designs that you're coming up with? Or do you have to, when you go to propose the Beyond the Decadal Survey,
right?
Do you have to have shown that, yeah, if we just had this 9-meter telescope, we could do this? Or do you just...
you mean planets in particular?
Well, I guess all of the science you're trying to do, is there something that can be done now with existing instruments to prove that this telescope, once it's built, will be able to do better? Or is it just not possible to do it right now? Is that an ill-formed question?
Well, I mean, you want to design an observatory where it's not possible to do now, because otherwise, why would you build it? So that's part of it, but
well, I guess, I mean, we're already...
Is there a sample? Is there types of objects? Yes. I mean, that is important for motivating the science question. So the science question might be, well, we want to understand if there's life on any of these things. But we're not going to hunt them down and try to figure out which ones have exoplanets. We're going to be relying on, and in fact, we're relying on the fact that, Hubble, James Webb, TESS, ground-based
Kepler,
systems are going to come up with a long list of potential targets, and astronomers who are expert in that are going to pick the ones that would be done with origins.
Right. And so, for example, if you take the example with planets, we ask, has this been done before? Like, well, yes. I mean, Spitzer, for example, has done planet transits in the infrared many times. In fact, the recent TRAPPIST-1 result, a lot of those planets were detected with Spitzer in a very long transit observation with Spitzer. So even Spitzer can detect Earth-sized planets in some cases. JWST will be able to measure the composition of atmospheres at similar wavelengths, but we know that it'll be difficult for JWST to get good enough signal to noise on many or most of these rocky planets in the habitable zone. So you do need something bigger than JWST, and so you can just kind of scale it. So like, okay, in principle, we could do this with JWST if we had 100 hours to do it, if we had 500 hours to do it.
I guess that's where I was going with it. Yeah, I just wanted to see if maybe Hubble even could be doing some work.
Well, there
if you had
are
infinite amounts
observations of planets, but as Klaus says, some of them are sort of, almost Earth-sized, but there are larger ones where this transit, the backlit stuff, all of those, there are hints that that's feasible with Hubble. And so with a larger telescope out in the infrared, it should be fine. It shouldn't be a question.
Right. So it's going from, it's like, okay, so if you have infinite amounts of time, you can do anything with a small telescope in terms of planets because it's a matter of collecting enough photons. Right? We don't have infinite amounts of time. So if you go from, okay, it will take us, hundreds of hours to do this planet, we build the origins, and it will take us 2. It suddenly becomes much more, within reach. And not only that, you can do a planet in 2 hours. You can do many planets then, and you can really start to get a sense of the sample of the universe, right? I mean, what do typical planets look like? Maybe you have to look at a lot of planets before you find any with life. We don't know that yet.
And also, I was just going to comment. It's like when Klaus was speaking earlier, saying, when, or Margaret, one of the two, is when we started with James Webb. It was like, oh, we knew, or maybe it was Alberto. I think it was Alberto. Actually, got to get the credit right. That we didn't know. We had a few exoplanets, but not a lot. Then all of a sudden, there's like exoplanets everywhere. Now we're seeing multiple planet systems. And I'm just amazed. I get in my inbox like a paper all the time from HARPS, ground-based telescope space. Now all these multiple planet systems are happening. And we got to look at all of those too and pick the ones that we can analyze in detail. So it's pretty exciting.
And so I'm going to make a prediction with JWST where we're going to have a situation in 10 years so that where JWST has found these, this is the way it's going to go. It's not going to be this big, split. There's life. It's going to be JWST has found these very interesting signatures in these cases. Yeah. We just can't, we need something more to tell what's really going on. And then people are going to say, well, where is the next bigger thing so we can, we can nail it.
Agreed.
Okay. Well, Jurek Mazino is asking, now that we've started identifying exoplanets, as you guys pointed out, do you think there's potential for geologists to start looking at the exoplanets for their geologic history, current activity, etc.? He's asking that because he's a geologist. So what do you think, guys? Are we going to be able to get more detail out of these? We're talking atmospheres, we're talking biosignatures, but what about the geology?
Wow.
It's I would say it's a challenge right now, right, to get to the surfaces of planets. I mean, one thing is if you look at gas giants or hot Jupiters, they don't have a surface, right? When you get to the rocky ones, we're pretty sure they have a surface. But if you do transit spectroscopy, the planet goes in front of the star, you never get to the surface. You just get the atmosphere. There's something you potentially can do in the mid-infrared. You can actually, maybe if it's not a lot of clouds, you can get to the surface directly. So I think that might be, if you talk about geology, well, that's one thing. It might get you directly to geology. At least you can measure surface temperature. Other things, I think, is volcanic activity. And that might be related to CO2 content in the atmosphere, maybe sulfurs, compounds.
So you can infer some of the geology based on what perhaps, you can see from the spectra of these exoplanets. Interesting.
Okay. Pretty much, but I would emphasize that people who do geology or planetology and stuff are really vital to interpret anything that we get. So in some sense, they're going to have some grounding in, well, what could create that? We might get a spectrum of, I don't know, we have sulfur, ammonia, and this. And we're like, well, what creates this? Well, it's not ozone and methane, so it's not life, but what could create this? And that's where geologists or planetologists really have a role in trying to figure out what is going on with these things.
Okay, Anand Dane is asking, and this is a good one for a future in space hangout. Deep Astronomy, what's the plan post James Webb in about 20 or 30 years? Which of you guys want to comment on that? Where are we looking? We've got James Webb coming up. We've got W first after that. We've got, hopefully, Origins.
Yeah, I mean, that's what we're talking about with Origins, is figure out what's going to happen after W first. That's the funding wedge, as to say, that opens up as W first gets built. At some point it's built, the money is becomes
available
in the budget, can be used for something else.
Now, are you guys going to be competing with the HDST? What are they calling it now? I don't even know what it is.
LUVOIR. They're competing with LYNX, which is the X-ray. They're competing with HABEX, habitable exoplanets. So there are 4 runners, right? So it's going to be an interesting competition, right?
Okay, so we've got a lot of So
may the best science win.
So, I mean, my hope is that at least one of these flagships is selected to be launched, because I think that there's been so much excitement, so many discoveries just with the current flagships that we're going to have more if we continue with this notion of having flagships that everyone can use. Everyone who has a good idea of how to use this gets an opportunity.
Yeah, but I would like to caution against thinking of this as a competition, right? Because we're not right. We're doing LUVOIR and HABEX are doing exoplanets. We're doing exoplanets. We're not doing the same kind of exoplanet science, right? You don't get the same kind of information out of an optical near-infrared spectrum of an exoplanet as you do in a mid-infrared. Mm-hmm. And there may be things like we talked about when you're getting to the surface of the planet. There might be things where you need both. Mm-hmm. And so if we really sell this as a competition. I feel we get too much infighting between scientific communities on a generational timescale. It's not necessarily something that.
That's a great point.
And to follow up on that, NASA headquarters made it very clear that this isn't a competition. NASA headquarters is not going to be picking any of these and telling the decadal, this is the one we want you to think about. They're saying, we want 4 good reports, and we want to hear what the decadal survey says about these reports and the ideas in them. And it could be, like I said, they come back and they say, we like all of them. We want you to do them all. One has to be picked first. Eeny, meeny, miny, mo. I don't know. I mean, but I don't think that...
Well, that's exactly what happened.
I was gonna say, at some point they're going to be saying, well, we can't pay for all of these. So in a kind of sense, it is a competition. But you're saying...
You have to pick an order, maybe, of what maybe makes the most sense to go first, because maybe one's easier to build and can be done now. Right. And the other one's not as easy to build, and so we like this, but it's going to take 10 years to get to where we can do it.
And what really helped W first was the fact that it could use that NRO chassis, and it was already on the decadal survey before, right? So that helped it a lot, quite a bit, get going. So I guess that's what you mean. So should something change where something becomes available that wasn't before, it might help a case, it might hurt a case. Things like that.
Also, I mean, the budget is not a zero-sum game. Like you can go back and you can do maybe one of the missions. So for example, something like LUVOIR, right, which has as its key science case to take an image of an Earth-like planet. Maybe that's decided that is so important that gets taken out as an Apollo type project for NASA. Right, so it gets taken out of the astrophysics.
That one piece of the science mission.
That one piece, we really have to do that. And so it gets put somewhere else, and you can do astrophysics for other things, right? Because the danger is as well that since these are generational things, we're working in the mid to far infrared, right? And so this is expertise that are now being built up with JWST. It's very much a similar kind of thing, the same kind of detector, same kind of technologies. When JWST ends, if that's not picked up by the next generation, we will lose this generational knowledge, right? If we have a 25-year gap in a certain area or certain types of technology, we won't be able to just pick that up again. It's just like the Apollo program, right? If we decided we wanted to go to the moon, we'd have to reinvent the wheel, right? A lot of the knowledge, know-how.
Well, they kind of are with SLS a bit, but yeah,
exactly. So I think it's important to try to convince the decadal survey that we don't want to lose, these big areas for a generation.
And I think Klaus is making a good point. I mean, more than, I guess I would not describe the decadal as a competition as I did before, which I think is correct. It's more of a sort of collegial exercise to set the path for the best science forward. And I think that's what ultimately will win. But as Klaus said, since missions take decades to complete, there is this danger that you might lose expertise in IR, in optics, in optical wavelengths, or so on and so forth, that might be needed for future missions. So it's a delicate exercise that the community has to play every 10 years.
All right. Well, this is kind of a growth field, wouldn't you guys say? I'll put this to the whole panel. A lot of young people watch these hangouts looking to get into astronomy. This is a great area to look into, not just to be an astronomer or a PhD level, but also to, like Alberto was just alluding to, you want to have expertise in programming detectors, for example, reading out cameras, processing data. You want those skill sets, right? Building things.
Yeah, absolutely.
Oh, absolutely.
So this is a good time to, and it's a golden age of astronomy for a lot of reasons, folks. One of them is we're learning more about the universe than we ever have before, but another one is that these technologies are enabling jobs for a lot of people who don't necessarily want to go in and become a PhD, but they want to be maybe an engineer or a software engineer, something like that. So
absolutely.
Yeah,
astronomy is really, it requires all fields of science and engineering to accomplish it.
And geologists too, Jurek. So get on it.
Absolutely.
Yeah. All right, guys. Well, we are out of time. I got to stop here, but I want to thank our guests. I want to thank Dr. Margaret Meixner from the Space Telescope Science Institute. She's a community chair for the Origin Space Telescope Study. Also, Dr. Klaus Pontoppidan, also from the Institute, Space Telescope Science Institute. He's a project scientist for JWST, as well as a member of the Origins Science Technology Definition Team. So thank you both very much for taking time out to join us.
Thank you, Tony, for having us.
Oh, it was a pleasure. Yeah. And good luck on the report and getting all the stuff done. I hope I don't want to say I hope you win, but it's I guess it's not a competition. But I hope you get a piece of whatever you're after, and I hope it comes to pass.
Okay.
So thank you for letting us know.
Thank you.
I'd also like to say thank you to our great audience. I mean, I think we've got some really excellent questions.
They are awesome. That's right. As the chat scrolls by, I am always impressed. So thank you all. Thanks to Galaxia, capital H, Jurek Mazino, Adam Synergy, John Shuffle, all of you guys. Thank you so much for taking time out to interact with our guests. Hope you'll join us next week, where Carol will be back, when I will be back with an Astro Coffee, and I'm really excited about this one. Has it all been confirmed, Carol? Can we talk about it? Maybe.
Yes, I just got the confirmation. I was furiously trying to make sure they were going to come. The Cassini people are going to come and talk about the Cassini mission.
Yes, so
I got them.
Awesome.
I've been like, please, are you coming?
So come back next week when we'll be talking about the Cassini mission. As you all know, it started its grand finale, where it will soon end its wonderful mission life, where it's done so much great science around the planet Saturn. And so we will be. What do you got there? What is that, Alberto?
The grand finale pin from
you got a
Cassini.
pin.
Oh, look at you!
I was at headquarters, and Jim Green gave it to me. It was a great present.
Oh man!
Awesome. All right. Well, okay. Well, thank you guys.
He's going to give that to me tomorrow.
Oh, that's right. You can.
Okay. Yeah, we'll need more than coffee. Like booze,
I guess
maybe.
not. I guess not. Maybe not. Maybe not.
All right. Okay, folks, I'm going to have to let you guys go. Thank you all very much for watching. And as always, keep looking up.